Okay, to plot this on the Argand diagram, remember the real axis is the horizontal axis. The imaginary axis is the vertical axis. Okay, so if things are real, they're grounded, the ground is horizontal. If things are imaginary, they can be up in the air, blah, blah, blah. Okay, this is the imaginary axis. So my real part of this is -1. So I'm going to be at -1 on my real axis and +3 on my imaginary axis. Okay, +3 was my imaginary part. So my Z is going to be here on the Argand diagram. Okay, and then it says Z with a line over it. So that's the complex conjugate of Z. Okay, so when it's the complex conjugate, we change the sign of the imaginary part. Okay, so if you didn't get it, take that down. Okay, so Z was -1 plus 3i. So the complex conjugate of Z is -1 minus 3i. Okay, so it's still -1 on my real axis, and now it's -3 on my imaginary axis, so it's here. Okay, so that's my complex conjugate of that. Okay, and then it says investigate if, and then it has a line on both sides of Z. Remember, when there's a line on both sides of Z, it's looking for the modulus. Okay, the distance from the origin. Okay, so we are checking, do they both have the same distance from the origin? Now you can use, if you prefer, the equation from the log tables for the distance, the length of a line, or the distance between 2 points. You can use that for, like, let's say, the point where Z is and the point of the origin, so 0, 0, and then do the same for the modulus. Or we can use Pythagoras and say, so for Z, first of all, we have a point, and let's say the origin is here. Okay, and it goes 1 across and 3 down. So we are finding the modulus of Z there. So we can use Pythagoras' theorem, which is a squared plus b squared equals c squared. Okay, so c squared in this case is the modulus of Z. So we'll have 1 squared plus 3 squared is the modulus of Z squared. Okay, so 1 plus 9 is the modulus of Z squared. So if I have the modulus of Z squared, how do I find just the modulus of Z? Well, I have to square root this side. Oops. Okay, so I have that 10 is the modulus of Z squared. So I'm going to square root to just get the modulus by itself. So square root 10 is the modulus of Z. Okay, and then I'm just going to do that exact same thing for the complex conjugate of Z. Okay, so the modulus of the complex conjugate, so it was a point like there in terms of the origin. So this here is my modulus of the complex conjugate. It went out 1 and down 3. So exact same thing again. We'll use a squared plus b squared equals c squared. So I have 1 squared plus 3 squared is equal to the modulus of the conjugates squared. Okay. So the hypotenuse usually in Pythagoras is the c. so the side opposite the right angle. So here it's always our modulus. Okay, so we're going to have 1 plus 9 is equal to the modulus of the conjugate squared. So 10 is equal to the modulus of the conjugate squared. So to get just the modulus of the conjugate, we are going to have to square root, and we will get that the square root of 10 is equal to the modulus for the conjugate there. Okay, so yes, they are equal. Needs to be written somewhere. Okay, so yes, the modulus of z is equal to the modulus of the conjugate of z, as square root 10 is equal to square root 10. Okay, this one you actually had, I'm fairly sure, like the exact same question as this and a solution to it from the 2020 paper. It tells us here, so given that I squared is -1, so if you didn't sub in -1 in part A, this might be a little reminder for you to jump back and fill it in. Investigate the value of each of the following. So we know that I is the square root -1, I squared is -1, I cubed is -I, because it's I squared times I1, so it's -1 times the square root of -1, or just a -I. And then I to the power of 4 is I squared times I squared. So it's -1 times -1, which is just 1. Okay, so I to the power of 4 is the nicest one for us to get things in terms of here, because it just means that we can replace them with 1. And we know when something multiplies by 1, it just stays the exact same. So I'm going to try and write this in terms of I to the power of 4 as much as possible. So I know that I to the power of 23 is the same as I to the power of 20 plus 3. So why have I split it into 20 here? Well, because I know that I to the power of 20 is the same as something like 5 times 4. Okay, so go back to the rules for indices in our log tables. When two things add together, it's the same as them multiplying. So I have I to the power of 20 times an I to the power of 3 here. Okay, so I to the power of 20. Why do I want things in the form of I to the power of 20? Well, because I can write that as 4 times 5. So 4 is the ideal thing that we're looking to write the i's in terms of here to simplify it down. Okay, and then we have I to the power of 3 still. So I'm going to write this as, and again we use our log tables here, I to the power of 4 to the power of 5. Okay, and then I to the power of 3. So I know here that I to the power of 4 was 1, so I'm going to fill this in. So that's 1, and then to the power of 5, and then I cubed, or I to the power of 3, is -I. Okay, so 1 to the power of 5 is just 1, and then -I. So 1 times -I is just -I there.